In advanced physics, you run into these problems that just seem impossibly tangled. But what if there was a way to just switch your point of view and suddenly everything becomes simple? Well, there is. Today, we're diving into what is basically a physicist's superpower for doing exactly that, canonical transformations.
All right, so here's our game plan. First, we're going to look at a messy problem to see why we even need this stuff. Then we'll get into the simplification tool itself, what the rules are, and how you actually generate these transformations. We'll even put one to the test. And finally, we'll zoom way out for the big picture perspective.
Okay, let's kick things off with that messy problem. We're about to see why picking the right set of coordinates, your mathematical point of view really, can be the difference between a total headache and a genuine breakthrough.
So, just take a look at this. We're looking at the exact same physical situation, a particle just going around in a circle. Now, on the left, we're using your standard x and y coordinates. The Hamiltonian, which is basically the recipe for the system's total energy, it looks pretty messy, right? But now look at the right. We switch our perspective to polar coordinates using radius and angle instead. And bam! The very same energy equation suddenly looks clean, elegant, and way easier to solve.
So the whole goal here is to transform our description from that complicated mess into something simple. We want to find a point of view where the important stuff that doesn't change, things like total momentum or energy, what physicists call conserved quantities, just pops right out at you. The more of those we can find, the simpler the problem gets.
And this is precisely why we need a formal method to make that switch. Which brings us perfectly to our next section, the simplification tool. We're talking about the canonical transformation itself.
So what is this thing? Really, it's just a special, very carefully chosen change of variables. We're swapping our old set of coordinates and momenta, the little q's and p's, for a brand new set, the big q's and p's. But here's the absolute magic trick. We do it in such a way that the fundamental laws of motion, what we call Hamilton's equations, keep their exact same form. The rules of the game don't change one bit.
And that's so important. We are not changing the physics at all. A planet orbiting a star is still, orbiting that star. All we're doing is finding a better mathematical language to describe that orbit, a language that makes the whole system so much easier to get our heads around.
Okay, that sounds great, but how do we actually pull this off without, accidentally breaking the physics? That is the million-dollar question, and it's what our next section is all about, the unchanging rules. All right, there is one non-negotiable, absolute #1 rule: the dynamics of the system cannot change, period. A circular orbit has to stay a circular orbit. The path the object takes, how it moves through time, has to be completely identical, whether you're using the old coordinates or the new one.
But that begs the question, right? It's one thing to say the dynamics have to stay the same, but how do we mathematically guarantee it? How do we build a transformation where we know for sure we're not breaking that fundamental rule?
Well, the answer lies in this really elegant piece of mathematics called the Poisson bracket. Think of it like this. It's a special operation that tells you how any property of your system, position, momentum, you name it, changes over time. If you want to know how something evolves, you just take its Poisson bracket with the Hamiltonian, the total energy. So in a very real sense, the Poisson bracket is the engine that drives the dynamics of the whole system.
So, if the Poisson bracket is the engine of the dynamics, then to keep the dynamics the same, we just have to make sure the fundamental structure of the Poisson bracket itself doesn't change. That's it. That's our guarantee. The Poisson bracket of our new coordinates, q and p, has to be exactly the same as it was for our old ones. It has to equal 1. Simple as that.
Okay, so we've got our fundamental rule. But, how do we actually cook up transformations that follow this rule? We can't just guess, right? So let's get practical here in our next section, generating the transformation.
Right, so instead of just trying things randomly, physicists just have this amazing toolkit. They're called generating functions, and you can think of them like mathematical recipe books. Each recipe is specifically designed to cook up a transformation that is absolutely guaranteed to be canonical from the start.
And there are 4 main flavors or types of these generating functions, as you can see here. Each one just uses a different mix of the old and new variables. So, for instance, the F1 type uses the old position q and the new position q. You just pick the type that's most convenient for your problem, follow a couple of simple steps, and boom, out comes your new simplified coordinate system.
Now, I know this might still feel a little abstract, so let's make it super concrete. It's time to put this all to the test. Let's see a canonical transformation in action.
All right, let's take a look at this example transformation. As you can see, it kind of scrambles the old position Q and the old momentum P to give us a new position Q and a new momentum P. So the big question is this thing legit? Is it actually a canonical transformation? Does it follow our one big rule?
Well, we can find out pretty easily. We just need to run our canonical test. It's a simple three-step process. 1, we've got our equations for Q and P. 2, we calculate their Poisson bracket. And 3, we see if that result is exactly 1. That's the whole test.
And when you actually do the math, what do you get? Well, the Poisson bracket of Q and P boils all the way down to cosine squared alpha plus sine squared alpha. And if you remember your high school trig, you know that always equals 1. So yes, it's canonical. And what's really amazing is that this works for any value of that parameter alpha. It's a whole family of valid transformations.
So we've seen what these transformations are and how we can test them. But so what? What's the big picture here? Why does this all matter? Let's wrap everything up by zooming out for a deeper perspective.
Look, the reason this is so important is because canonical transformations are way more than just a clever math trick. They are a genuinely profound tool. They let us take problems that look absolutely impossible and make them manageable. They are the key to unlocking those conserved quantities we talked about, like energy and momentum. And by doing that, they often reveal these deep, hidden symmetries in the laws of nature, showing us that there's a more fundamental and, honestly, a more beautiful structure to the universe than we first thought.
It all just comes down to the power of finding the right perspective. And it really makes you wonder, doesn't it? What other physical laws, what other parts of our universe that seem incredibly complex right now are just simple ideas waiting for us to find the right point of view, the right transformation, to finally reveal their true simplicity?